All right, thank you, Adam. Next up, we have Matthew Hebert.
Get that right there. Then get you a printed copy. That's
Yeah.
something to get you
What
on.
was the email that you sent? There was nothing in the email. You just said late.
Yes.
I thought you were going to be late for the class. That's right. There you go. That's your textbook.
That's long gone.
Good book. You should keep it.
Hey guys, I'm Matt, and I'm here to talk to you about the Rankin cycle experiment. First, I'm going to give you some background information about what happened with Rankin. And William John Malcolm Rankin was back in the late 1800s, and he came right after our boy Kelvin, who had just invented Kelvin. He decided that he was going to invent Rankine, which is kind of a copy because the Rankine number is just converting Fahrenheit to Rankine instead of Celsius to Kelvin. So he was in the time of where the steam engines were getting big and thermodynamics really blossomed at that time, because that's basically when the field was started. Also our boy Clausius was in there. They were around the same time. And he helped contribute to the second law of thermodynamics. So what Rankine did was he made a cycle that idealized a working fluid and basically got it to evaporate and condense continuously. That's basically what the Rankine cycle does. You'll have in your Rankine cycle, you'll have four main components. You have a pump, boiler, turbine, and condenser. And the main point of it is to convert heat and power into mechanical work from your turbine. So just to give you this is actually pretty useful. I'll come back to it. So just to give you a run through of the TS diagram of the Rankine cycle. You're going to start off with your fluid coming into your pump. It's going to isentropically compress and go from your pump to your boiler. Your boiler is going to heat that up in a constant pressure process to superheated steam. And from there, your turbine is going to come in and isentropically get work out and put the pressure or the temperature down, and it's going to come back into the pump. So all that helps you understand that. So why is this relevant? The Rankine cycle is a fundamental operating cycle. All thermal power plants where liquid is constantly evaporated and condensed. Clausius did the Carnot cycle, and it's a little bit different than that because that's a little more well-known of a cycle. It has no isothermal processes. It's more rapid. It has a lower efficiency than the Carnot cycle. The Carnot cycle is the best engine you can get. This isn't necessarily that. So this is when it comes to our experiment that we'll be doing, this is the apparatus we'll be looking at. You'll see we got turbine, condenser, boiler. We got, I think, a few pumps in there. Basically, for this experiment, we're going to be reading just like the refrigeration experiment. We're going to be reading values at different gauges. The gauges in this experiment are absolute pressure gauges, so keep in mind with that. Gauge pressure readings, not absolute pressure. So keep that in mind when you're going through an experiment. And what it's going to look like is it's going to be like old school thermal problem. Like we're going to get properties on the side, and we're going to have to get efficiencies out of that, just like the Ready's class. So these are the objectives you'll be calculating, like mass flow rate, work by the pump, whole boiler heat input, the heat removed from the condenser, the turbine work, turbine efficiency, and cycle efficiency. So you're going to be getting the 6 pressure measurements from the gauge valves, the 6 temperature measurements from the selector switches. We're going to be given the generator output using the multimeter, and we're going to be given the flow rate, the measure system flow rate with the flow meter in the experiment. So these are just some useful equations. Remember that to change to Rankine when you're doing all these. I'd end up not using that R water for my calculations, so that's not even useful. But here's some useful equations. And I was thinking for the end I would show y'all how to calculate all this. Here's my calculations, and I have an error, but I will get to that. So basically, we're given our diagram, and we're given that going into the pump is going to be saturated liquid. This is going to be the condenser, and it's going to go so this right here is the turbine, pump, boiler, and condenser. And basically what's going to happen is, in order to, we're going to put out our energy equation first, because everything else cancels out. So for instance, with your pump, you're going to have your heat go out to 0. Your dW is going to be du. So what is your du? Your du for a controlled mass is you're going to have to include enthalpy. So it'll be your dH minus your Vp. And but in this case, we're just going to in this case it all comes down to enthalpies. It's going to be work for the pump is going to be the enthalpy between 1 and 2. So it'll be work in, it's going to be, and you're going to do that for everything to get what you want. So the turbine work out, which is extremely important in your efficiency, is just going to be your change of enthalpy between those two. So to calculate the final efficiency of the cycle, it's going to be your net work over what you put in, which is your Qn, which is the heat going into the boiler to heat up everything. So your work net is going to be your turbine work out minus the work you put into the pump divided by your heat. And that's going to be how you do this problem. Where I messed up on my calculations was finding my work for your pump. I should have just used the change in enthalpies. And the confusing part with all this is in the calculations, I wasn't given the values, so I had to relate these isentropic processes where through the pump, through the boiler, S2 is going to equal S3, or no, through the pump, S1 is going to equal S2. Through the boiler, isentropic processes. Okay, so the pump is going to be isentropic. The turbine is going to be isentropic. These two are going to be constant pressure, and you're going to have to relate those values on your tables to solve these and get your enthalpies and solve these problems. So that's it.
You are a minute and a half over. Are you done or are you still going?
Yeah, I'm done.
You're done. You're a minute and a half over. So again, what is the mistake you made? What is the mistake with that equation? Anybody? He made a mistake and he tried to wiggle himself out and come to the correct solution. Well, you start with the cardinal mistake.
All right, with what's written right here.
Now, what is the very first equation that you wrote down? Q minus W squared delta U is the first law for what? For what kind of system? Closed system, which is a controlled mass. What else? Compressors and pumps and turbines are controlled.
Mass.
Are controlled.
Control volume.
Control volume. So what is the first law for control volume?
Right here.
No, it just says control mass. That's the first law for a control mass. What is the difference in a control mass and a control volume?
In control mass, the mass is constant.
Uh-huh.
The volume is constant.
So in a control volume, what can go in, what can leave?
Matter or mass.
So in a pump, does water enter or water leave?
Yeah.
Yes. Okay, is that a control volume?
Yeah.
Okay, what's the first law for a control volume then? Don't just
This
point
would
at
be
that.
good for control mass.
That's the control mass. Yes, we just said that. What's the first law for a control volume? Energy in is equal to energy out.
Right.
Energy going in is Q plus enthalpy in plus kinetic energy in. So what is the energy that's going in? Heat going into a system, Q, plus enthalpy plus kinetic energy that's going in, plus potential energy at the inlet is equal to energy outlet, which is work plus enthalpy at the outlet plus kinetic plus potential. We neglect the kinetic and potential. Q is 0.
Right.
Work then ends up being difference in enthalpy.
Enthalpy.
You wrote down the first law for a control volume and then you decided I'm going to have some TDS equation. BH is equal to TDS plus BDP.
That was when I was figuring out the constant.
No, you knew what the answer was. You knew you had to get enthalpy, right? And you start off something wrong and you
Yeah.
work your way to get it there. Then you said a couple of things. Go back to your picture of your diagram. Do you see the difference between the first law between the two cases? Because it has a different notation. This equation here. 3, not like this, diagram it. Location 3 is saturated
Vapor.
vapor. Why is it not superheated?
Oh, because when they gave us an example, like when I was supposed to do my calculation, they said assume to go to saturated vapor. So I could get the value from it when I was doing my calculation.
And then you said, what is, okay, draw a Carnot cycle for me.
Carnot?
Because you use the word Carnot cycle does, Carnot cycle has constant temperature processes and Rankine cycle doesn't.
Isothermal.
It's a thermal, constant temperature.
Yeah.
No, there is a constant temperature process right here. Within that diagram. 4 to 1, what is constant?
That's the condenser. Well,
4 to 1, what is constant?
it's constant because it's in the vapor dome.
So there you go.
So temperature. Yeah, that is. So what I said was wrong about the Carnot.
No, I mean, you can have an ideal Rankine cycle that stays within the dome. That's what, so the Rankine cycle that stays everything in the dome is called ideal Rankine cycle, right? But we don't build a Rankine cycle like that because location 4 is partly vapor and partly liquid.
Right,
And
right.
why is that not a good thing?
Because
Bad for you? But no, what is, no, 3 to 4 is what you want. Turbines, it's bad for the turbine blades. Bad for the blades, correct? Blade, which is why we try not to have location 4 to be saturated liquid or
Right.
mixture.
So in the example that I
I don't know
did
why would they do that. I don't know what, I can't believe that our Rankine cycle that we have
wasn't in the superheater.
can't be because the blades will be breaking with it. We don't use it that much, but it's
So
not a good design.
I chose this graph just because it gave me that the third point was saturated vapor.
That's fine. I'm not-
in the lab sheet.
You could have picked the 4th point to be the saturated liquid. That still would work.
Yeah, I would have loved to do that.
Fine. But I'll make you do it then. It's just easy.
That would have made it way better, actually.
Let's follow what I mean, just as straightforward. Okay, next.